Most people outside the United States assume American houses are weak. Visitors often describe them as flimsy or compare them to cardboard boxes because the walls are made of thin wood studs instead of solid brick or stone. This assumption is common, but it does not match how these houses are actually engineered, tested, or how they perform under real stress. The comparison usually starts with brick. In many parts of the world, especially Europe, houses are built with brick or stone walls that carry the weight of the structure. These walls look solid, and they are very strong under one specific type of force: compression, meaning weight pressing straight down. A well-built masonry wall can support enormous vertical loads for centuries. This is part of why old European stone buildings have survived for hundreds of years, and why people associate brick and stone with permanence and strength. But strength is not one single quality. Engineers measure materials against several different kinds of force, not just the weight pressing down on them. Buildings also have to resist bending, twisting, and sideways pressure from wind or shaking ground. In these categories, wood performs very differently from brick, and often better. Wood has a high strength-to-weight ratio. This means that for its weight, wood can bend and flex under pressure without breaking, in a way that heavy, rigid materials like unreinforced brick generally cannot. When a strong wind pushes against a wood-framed wall, the structure can flex slightly and absorb some of that force. A rigid masonry wall does not flex in the same way. Instead, the pressure has to be carried entirely through the material's own strength, and if that pressure exceeds what the wall can hold, it can crack or fail more suddenly, especially if the masonry was not reinforced with steel. This difference matters most in two specific situations: earthquakes and high winds. In an earthquake, the ground moves rapidly back and forth, shaking whatever is built on top of it. A structure that can flex slightly with that motion is generally able to absorb and dissipate the energy of the shaking. A structure that is stiff and heavy, without reinforcement, is more likely to crack under that same motion because it resists the movement instead of absorbing it. This is a major reason wood framing became the standard building method across the western United States, where earthquakes are common. After the 1994 Northridge earthquake in California, engineers noticed that many wood-framed homes had suffered damage that researchers did not fully understand at the time. In response, the Federal Emergency Management Agency funded a multi-year study known as the CUREE-Caltech Woodframe Project. Researchers built full-scale wood-framed structures and tested them on shake tables that could simulate real earthquake motion. The project studied how walls, connections, and entire houses responded to seismic force, and used the results to improve national building codes for wood-framed construction. One structural engineer involved in the research noted that about 99% of homes in California are built using wood framing, which is part of why understanding and improving its earthquake performance mattered so much. The research did not conclude that wood framing was inherently weak. It concluded that specific connections and details needed to be engineered more carefully, and those findings were built directly into the codes that govern how houses are built today. Hurricanes present a different kind of stress, but wood-framed construction has been engineered to handle that too. A modern wood-framed house built to current code in a hurricane-prone region includes several specific reinforcements that did not exist in older homes. Metal hurricane straps and clips connect the roof to the walls and the walls to the foundation, so wind cannot lift the roof away from the rest of the structure. Windows are rated to resist impact from flying debris. Garage doors are reinforced, because a failed garage door can allow wind to enter the house and blow out walls from the inside. Shear walls, which are wall sections specifically braced to resist sideways force, help stabilize the whole frame. Together, these features allow a modern wood-framed house to resist winds well above 130 miles per hour, which covers the range of a major hurricane. It is worth being precise about what is actually being compared when people say American homes are made of wood, while European or Asian homes are made of brick. In most of those countries, the exterior wall itself is structural brick or block, meaning the wall is literally holding the building up. In the United States, many houses that appear to be brick from the outside are actually wood-framed structures with a layer of brick attached to the outside as a facade, similar to how vinyl siding or stucco is applied. That thin brick layer improves appearance and offers some wind resistance, but it is not what holds the building up. The wood frame underneath is doing the structural work. This distinction is important because comparing a true structural masonry wall to a decorative brick veneer is not actually comparing the same kind of construction. There is also a fire safety point worth clarifying. People often assume brick homes are inherently safer in a fire because brick itself does not burn. This is true for the exterior walls. But most homes, including brick ones, still use wood for their roof structure, floor joists, and interior framing, because wood remains one of the most practical materials for those parts of a building regardless of what the exterior walls are made from. This means the fire risk difference between a wood-framed home and a brick-faced home is often smaller than people assume, because both structures typically contain a large amount of wood in places the eye cannot see from outside. None of this means every wood-framed house is automatically safe, or that masonry construction has no advantages. Reinforced masonry, where steel bars run through brick or concrete block and the whole wall is engineered as a system, can perform very well under wind and even under some seismic loads. But that kind of construction requires more specialized engineering and skilled labor, which raises the cost and the time needed to build it. Unreinforced masonry, built without steel reinforcement, is the version that performs poorly under earthquake or high wind stress, and it is this older, unreinforced style that often comes to mind when people picture solid brick construction. The choice between wood and masonry in different countries has as much to do with regional hazards, available materials, and cost as it does with which material is objectively stronger in every situation. In the American Midwest, where earthquakes are more of a concern than hurricanes, wood framing is the standard because its flexibility performs well under seismic stress. In parts of the American South and in Florida specifically, where hurricanes are the dominant risk and earthquakes are rare, many newer homes are built with concrete block walls because that material performs better under sustained high wind. Builders and engineers are not choosing wood out of habit alone. They are choosing the material or the combination of materials that performs best against the specific risks a region actually faces. Building codes in the United States also play a direct role in ensuring wood-framed homes meet clear safety standards. The International Residential Code sets requirements for wind loads, seismic loads, and structural connections based on where a home is being built. A wood-framed house built today under current code has to be engineered to withstand the specific hazards common to its location, whether that means high wind, seismic activity, or heavy snow loads. This means a modern wood-framed house is not simply a collection of studs nailed together the way early 19th century balloon-framed houses were. It is a system of engineered materials and connections, tested and refined over decades of research, including the direct aftermath of real disasters like the Northridge earthquake. It also helps to look outside the United States for a moment. Japan is one of the most seismically active countries in the world, with frequent and sometimes severe earthquakes. Despite this, wood framing remains common in Japanese residential construction, particularly for single-family homes. Japanese building codes, which are among the strictest earthquake codes anywhere in the world, still allow and often favor wood-framed houses because the material's flexibility under seismic stress is well understood and well tested there too. If wood framing were simply too weak to trust, a country with Japan's level of seismic risk and engineering precision would not continue to build so many homes with it. The cardboard box comparison itself is also worth examining directly because it is usually based on watching a house under construction before the walls are finished. At that stage, a wood-framed house is just a skeleton of exposed studs, with no drywall, no insulation, no siding, and no structural sheathing attached yet. It genuinely looks light and exposed at that point. But that is an incomplete building, not a finished one. Once plywood or oriented strand board sheathing is nailed across the frame, insulation is installed, drywall is hung, and siding or brick veneer is applied, the structure behaves as a single connected system, not as a loose collection of thin boards. Judging a wood-framed house's strength by its appearance mid-construction is similar to judging a car's crash safety by looking at its bare frame on the factory floor before the body panels and safety systems have been added. Tornadoes are sometimes raised as evidence that wood-framed homes are fragile, since tornado damage in the American Midwest and South is often severe and highly visible in news footage. It is true that a direct hit from a strong tornado can severely damage almost any above-ground residential structure, including brick and concrete ones, because extreme tornado wind speeds can exceed what typical residential codes are designed to withstand. This is one reason tornado-prone regions often emphasize underground or reinforced safe rooms rather than relying only on the strength of the exterior walls. The severe damage seen after a major tornado is not unique to wood-framed construction. It reflects the extreme force of the storm itself, a force that can also severely damage masonry buildings not specifically engineered for that level of wind. Longevity is another point worth addressing directly, since people sometimes assume wood cannot last as long as brick or stone. In reality, many wood-framed buildings from the 1800s are still standing and occupied today, well over a century after they were built. Wood does require maintenance to prevent rot, moisture damage, and pest issues, but masonry requires maintenance too, since it can suffer from cracking, water infiltration, and mortar deterioration over time if it is neglected. A wood-framed house that is properly built and maintained can last well over 100 years, which is roughly the same range often cited for well-maintained masonry construction. Insurance data offers one more useful angle on this question. Insurers do not price policies based on vague assumptions about which materials sound stronger. They rely on decades of claims data and engineering standards to assess actual risk. In earthquake-prone regions, insurers often view well-built, code-compliant wood-framed homes favorably compared to older, unreinforced masonry buildings, precisely because of how each material tends to perform when the ground shakes. In hurricane-prone regions, insurers pay close attention to specific reinforcement features, such as hurricane straps, impact-rated windows, and roof-to-wall connections, rather than judging a home purely by what its exterior wall is made from. A well-built, code-compliant wood-framed home and a poorly reinforced brick-faced home can end up with very different insurance outcomes, regardless of which one looks more solid from the street. There is a simple way to picture why strength to weight matters so much in construction. A structure's own weight is a constant force acting on it at all times, even before any wind or shaking is added. A heavier structure, like unreinforced brick or stone, has to work harder just to support itself, and any added lateral force from wind or seismic motion is added on top of that existing load. A lighter structure, like a properly engineered wood frame, starts from a lower baseline of stress, which gives it more capacity left over to absorb additional forces like wind gusts or ground motion before it reaches its limit. This is part of why engineers describe wood as having a favorable strength-to-weight ratio, and why that property becomes especially valuable in regions prone to earthquakes or high wind. So the idea that American houses are weak because they are made of wood does not hold up under closer examination. Wood is not inherently weaker than brick. It is different, with its own strengths and its own vulnerabilities, and modern wood-framed construction has been engineered over more than a century to work around those vulnerabilities. A brick or stone wall carries weight extremely well, but performs poorly under sideways stress unless it is reinforced with steel. A wood frame carries less raw compressive weight, but flexes and absorbs sideways stress from wind and earthquakes far better than most masonry can. Neither material is simply better in every situation. Each one is suited to different risks, and American builders have spent nearly 2 centuries refining wood framing specifically to handle the risks most common across the country.